Welcome back to Multivariate Calculus. In this video, we are looking at line integrals of vector fields. We've talked already about line integrals. Again, the name line integral is far and away more common, but thinking about this as a path integral, I think is more evocative. When we say line integral, we mean it's a one-dimensional idea, not that it's a straight line. We can go across any kind of curve or arbitrary shape that we want, as long as we can parameterize it. R of t, which we can give in 2 dimensions, or we can give in 3 dimensions, depending on the needs of the problem. We'll do a lot of work in 2 dimensions here because it's a little bit easier to draw, but we'll look at a couple in 3 dimensions as well. Now, a vector field is something that we've talked about, but not really looked at in a lot of detail. Let me get my head out of the way and let's talk a little bit more about that. A vector field is a function, which I'm going to denote capital F with a vector symbol above it to denote that this thing is in fact a vector. And we can go from R2 to R2, or we can go from R3 to R3. If you go onward beyond the study of calculus, you might see higher dimensional vector fields. That's just as valid. The thing that has to happen is that the dimension of the domain and the codomain has to be the same. So 2 and 2, 3 and 3, 7 and 7, whatever it happens to be. And a vector field consider this one, for example. F of x and y is equal to y opposite of x. If you sketch out some coordinate axes, so let's make that a little bit bigger even. No, I was right the first time. Well, at the point 0, 0, the vector is 0. At the point 1, 0, y is 0, x is 1, so we get 0, negative 1, which is going something like that. At the point 1, 1, we have 1, negative 1, which looks something like that. At the point 0, 1, we're going to have 1, 0, which looks something like that. And we can keep filling in. To get a sense of what this vector looks like at various points in the plane. If we go out, we'll end up with larger vectors, but the process is going to actually look basically the same either way. So a vector field assigns at every point in the curve, or every point in space, a vector. We've mentioned a specific kind of vector field previously. That was the vector field that was created by evaluating the gradient of a scalar function. Vector fields that are formed that way are called conservative vector fields. We're going to be talking a lot more about them. But the idea that I want you to think about that I mentioned then, when you see the words vector field, I want you to think force. Because if you've studied physics at all, you've studied um, Newtonian physics, you've studied the idea of a force, you have some idea of what we're talking about there. And so think about this as the force on an object. If you have a particle here, you can see that the force is going to cause it to move out. And then the force is going to cause it to move at a diagonal, and the force is going to cause it to move down, and the force is going to cause it to move at a diagonal. And you can track by calculating the force at every point and trying to bring it all together, what's going to happen to the particle. Sometimes force diagrams like this can be a little bit deceiving. It kind of looks like this particular particle is going to see a spiral outward, which is not actually the case. This particular force field causes particles to move in concentric circles. Um, but that's what we're looking at when we're talking about a vector field. And so if we talk about a line integral on a vector field, that means that we are starting at some point, we are traversing to some other point along some path, and we're asking how much does the force push on us on that path? Right? And that's the idea of work. Depending on how calculus intensive a previous physics course that you took was, you may have seen work described as force times distance, or force pushing in the same direction as motion, which you may have seen described using the dot product. And I was getting a little bit ahead of myself. We can take that motion and break it up into a whole bunch of tiny little coordinates and talk about how things move on each of those tiny little pieces. We'll call each of those little pieces some dr for the total motion being r, and then we'll add them all together to get the total amount of work done. Now, what is dr? Well, we can think about it uh, graphically. We can break it into components. dr is the vector with components dx, dy if we're talking about two-dimensional motion, or if we want to bring it into three-dimensional motion, we can talk about dx, dy, and dz. Either way is perfectly effective, although sometimes a little bit challenging. For example, if I want to calculate the work done by the force field, F of x and y is equal to y opposite of x, along the path given as r of t equals t squared for t between 0 and 2. Well, that's the force field that I just drew, so we have that picture. I can come up here and talk about it. The path t squared is a parabola, so we can draw that and we can have some idea of what's going to happen. And if you look at the picture, it looks like the field is going to be mostly perpendicular to this path, so we probably won't expect to see much. But we do know that it starts at t equals 0, which is going to be the point 0, 0. It ends at the point t equals 2, which is 2, 4. So we have something we can work with. All right. But our formula says that work is the integral along a curve of f dot dr. And f is, of course, y minus x. And dr is, of course, dx dy. And so we get the integral over our curve of y dx minus the integral over our curve of x dy. Or we could write that as a single integral, but it feels weird to have a dx and a dy in the middle of the integral. And suddenly we're stumped. Right? There's no obvious way of where to continue from here. Because we don't have y as a function of x, and we also don't have x as a function of y. Although we do have x and y both as a function of t. So dx is x prime of t dt, and dy is y prime of t dt. So if we go back to our path, x of t is t, and y of t is t squared, which means that x prime of t is 1, and y prime of t is 2t, which means that I can rewrite this integral as the integral t goes from 0 to 2 of y, which is t squared, times x prime of t, which is 1, times dt, minus the integral t goes from 0 to 2 of x, which is t, times y prime, which is 2t dt. Integral from 0 to 2 of t squared, that's going to be 1/3 t cubed. And then we have 2t squared, which is going to give me 2/3 t cubed. All right, 2 cubed is 8, so we're going to have 8/3 minus 0. We're going to have 16/3 minus 0. 8 minus 16 is -8. So the work done by this force on this path is -8/3. calculate the work done by the force field F of x and y is equal to y opposite of x along the path r of t is 1/2 t to square root of t for t between 0 and 4. One thing specifically that I want to point out here, r of 0 is 0, 0, and r of 4 is 2, 4. So the path that this particle is going to take is very different from the path that the previous particle took, but it's the same force field and it's the same beginning and ending point. So I would like you to examine whether the work done by a force field depends on the path taken or depends on only the endpoints. So look at same process we saw before. The particular path is a little bit different. It'll make the calculations a little bit messier, but it's the same basic idea. Take a few minutes, see what you can do with this problem, and I'll see you in the next video.